Welcome to 56th lecture in the course of Industrial Engineering and Operations Research. Now this is the last module of the course, and we will discuss in somewhat detail about various type of inventory models. So in this model, we will discuss about deterministic models as well as probabilistic models. We have already discussed something about inventory management, but inventory is a very important topic of industrial engineering. In industry, lot of cost saving can be done by minimizing the inventory. Therefore, this topic is given special importance. So, therefore, we will again revisit whatever that we have already discussed in the inventory models, and plus we will expand something. So, the deterministic model I have taken from various sources, and probabilistic models will be mostly based on H.A. Taha, because probabilistic models you may feel little bit difficult also because of the concept of probability. So, we will go very slowly and we will devote basically 4 lectures on probabilistic model. On deterministic model we will try to finish now itself. Okay. So, about inventory, what is inventory? It can be defined in various ways, but it can be also said that it is an idle resource of an enterprise. So, it is a resource which is not giving me anything, it is just occupied, and it is our money is locked up there. Okay. So, there are various type of inventories. We can define something called fluctuation or buffer inventory. This is the extra inventory a business holds to mitigate the risk associated with fluctuating demand or supply chain disruptions. So, we need buffer because we are uncertain about the situations, that is why we just keep this inventory, and in such type of inventory modeling, probabilistic concept may be very useful. Other type of inventory is called anticipation inventory. This is the extra stock a business holds to prepare for expected increase in demand. So, it is based on anticipation, your guess, such as during seasonal peaks or product launches. So, suppose you anticipate that this time there will be heavy rainfall. So, therefore, lot of umbrellas should be kept in the stock. This type of anticipation you make. Then another one is called cycle, or this is lot size inventory. This is the average amount of inventory a business holds due to ordering or producing in batches rather than strictly meeting immediate demand. So, we produce in the lots, that is called lot size inventory. We have already discussed something about that. Then transportation, or it can be called pipeline inventory. These are the inventories, that goods that are currently being transported from one location to another within a supply chain, such as from a supplier to a warehouse or from a warehouse to a retailer. Suppose some scooters are being produced in Faridabad, and from Faridabad to Guwahati, those scooters are coming. They are coming in a truck, and truck may take about 10 days to reach here, and then naturally that inventory is there, but it is in transportation. Decoupling inventory. The inventories needed to reduce the interdependence of various stages. That means it should not happen that some stage of the production suffers because of the lack of proper raw material. So, that is why we need to keep some inventories. So, if this is done, then it is called inventories needed to reduce the interdependence of various stages. We have already told you very simple formula, that is called economic order quantity, and the formula was like that. It is under root, and then in numerator you write 2 into setup cost or ordering cost, that how much this one and you need, and maybe we multiply by annual demand. So 2 into setup cost in rupees, annual demand may be how many units you are doing, and in the denominator you will have annual carrying cost per unit. Per unit carrying cost is how much. Okay. We also indicated you that in simple economic order quantity model, whenever that total setup cost is equal to total holding cost, then you understand that the optimum has reached. So by that also it is very simple that within seconds you can get the answer, but I am here again doing in a different way. Suppose total inventory cost TS is given by, you write the total inventory cost only. Suppose D is the annual demand, so and S is the setup or ordering cost, and let us say Q is the order quantity. So therefore D by Q times order will be placed. Okay. It may be fraction or whatever, but you know total demand is D, in one time you get Q, therefore number of times you have to order will be D by Q, and each time you order you have to encounter setup cost, therefore D by Q into S plus Q by 2 into H. Average inventory is Q by 2, we assume here that demand is constant, and you know gradually every inventory is consumed, and we are also, once it is consumed then we order. So therefore this is plus Q by 2 into H, and H is the annual holding or carrying cost per unit. So it is basically per unit. It is important to say that per unit, not that you should confuse this one. So you can say H is annual holding cost. That is why we have multiplied by Q by 2. So Q by 2 into H will be total holding cost. Now if this type of expression we have written and we want to find out what value of Q I should do, you see these expression that if you order more quantity at a time, then you have to spend lot of money in holding it. It will just occupy your space. But if you put a very small value of Q, then you have to order many times. That means your ordering cost will be going. So therefore, to these two conflicting things are there. Therefore, there should be one something in between. Therefore, we differentiate TS with respect to Q and equate it to 0, because minima or maxima is obtained by that condition. So we say DTC by DQ is equal to minus DS by Q square, okay, plus H by 2 equal to 0, or you get Q is equal to under root 2 DS by H. So you have found out. You can also verify that it is indeed minimum by taking the double derivative. That if you take the double derivative and you put that value of the Q, you will see that it will become positive quantity. Even here you can see that if I differentiate it once, this portion, second portion will become 0. In the first portion you will get ds by ds by q cube. That means suppose you differentiate it. So ds by q and 2 ds by q. So therefore this is positive, quantity is positive only, everything is positive, therefore there is a minima. So double derivative will give you minima. This will be equal to d square Tc by dq. Okay. Even if you don't do double derivative, you can also observe that of course at q is equal to 0, this is basically infinite. So that maxima side it may not be bounded, okay. And if you even q is equal to q also, if you can keep increasing as large as you want, so this portion will become 0, but the other portion will go very high, it will blow up. So therefore there is no chance that this type of expression can give you maxima, it will only give you minima by observations also, but I can tell you that you can double differentiate that thing. So anyway, once we have found that q, we can put it that optimum value as a q star also if you want. Q star is equal to under root 2 ds by h, and then you substitute in the total inventory cost, that is annual cost. So TC is equal to ds under root h by 2 ds plus ds by 2 h, and this comes out to be under root 2 ds h. So this is how that total cost has come. And if you want to say that how much is the setup cost will be half that, and similarly the holding cost will also be half that. If the setup cost is S plus BQ, then there is no change in economic order Q. Sometimes setup cost is dependent on the quantity. So we can say that suppose S plus BQ, some fixed component plus BQ. However, when you differentiate that thing, then you will see that it becomes a constant term, because once you put S plus BQ, so QQ gets cancelled, you get a constant term, and therefore it is not dependent on that. Then EOQ remains same. EOQ model with no shortage and several runs of unequal length. Sometimes unequal type of periods may be there, that suppose you have to average inventory is suppose half Q only, but this is held only for T1 period, and into holding cost, then it is half Q T2 into T2 time, and plus like that half Q Tn into H. If you take half QH common, then T1 plus T2 every time period will be added, and this will be total time actually T. So you get half QH, and this type of way you can do. Sometimes we have many items, that is multi-item deterministic model. So here the total cost will be, for each item you have to add the inventory cost and it will be obtained. So it will be I is equal to 1 to N, and this will be Qi by 2 into Hi plus Si into Di by Qi. Now in this there may be some upper limit on total inventory cost. You may say that yes, inventory cost cannot be more than that. So we can say that suppose I is equal to 1 to N, and we take some quantity Qi of any object, and into CUI, that is unit cost of that item. So if you sum these type of things, like you say CU1 into Q1 plus CU2 into Q2 plus dot like that CUN into QN. So this will be the total cost, and this should be less or equal to K, where the K has been emphasized. So now if this constraint is also there, then this becomes constraint optimization problem. Objective function is TC, that means you have to minimize TC, and the constraint is this. But I told that in constraint optimization problem, you can also try to solve it by, you can do that, and but if I make equal, that suppose I say that this is equal to K, okay, that means I take the border case, okay, I can keep this thing, then we can do it by Lagrange multiplier method. In that we put the objective function plus lambda is the Lagrange multiplier, and this is the constraint, okay. So this type of Lagrangian we have written, and this I will be differentiating with respect to various values del L by del Qi etc. That means there are n items, so for each one, and also you will differentiate by del L by del lambda equal to 0. So you will get back that this type of equation, and then you have to solve these values. So this method can also be employed, okay. Now let me just introduce two terms, that is say suppose marginal efficiency of capital. Firm should invest in those alternatives that provide greater return than capital cost to borrow. So marginal efficiency of capital, MEC, is the expected rate of return on an additional unit of capital investment, that is called marginal efficiency. That means you already invested 1 lakh rupee, again you will invest 1000 rupee, then how much return you will get. So it is return on capital or assets is defined as profit divided by capital. It can also be written profit by sales into sales by capital. Profit by sales is called profit margin. This is called profit margin. So this terminology you understand, that suppose I sold some item, okay, in 200 rupees, and but I got only profit as 100 rupee. So then my profit margin will be 0.5, okay. So, this is the thing, and multiplied by sales by capital. So, this sales by capital will be called capital turnover. I implied a capital of say 100, but I got a sales of 200. So, my capital turnover is 2. So, these are the things. Okay. Now, let us talk about other type of situation. Till now we considered only that demand is constant, it is not changing, but there can be dynamic demand models also, where demand is different in different months, so or different weeks. So, you have to decide the optimum inventory policy. So, dynamic demand models, these models consider how dynamic demand impacts inventory management decisions, especially for products with deterioration or seasonal demand, okay, because they have seasonal demand. An increment cost model analyzes the additional expenses incurred from a specific business decision, like producing more units or undertaking a new project, then how much it will have impact, that is called incremental cost. So, dynamic demand model helps forecast demand pattern, and incremental cost model helps optimize cost given the demand pattern. So, you have to get that, and we can write a simple dynamic demand model like this: dt is equal to A minus BPT plus C dt minus 1 plus epsilon t, where dt is the demand at time t, pt is the price at time t, dt minus is the past demand, epsilon t is random error term. So, we have tried to fit a linear model here. There is some constant term also in demand, but we have minus BPT, that means if the price, current price will be more, then demand will be reduced. That is why we have put a negative A minus BPT plus C dt minus 1. That means demand is dependent on the past demand also. So, some coefficient C we have implied, and epsilon t is basically some random error terms, because it is not possible that you put a formula and you get the right answer. So, we have put epsilon t. So, here demand today depends on today's price and previous demand. That means this is the objective, but you can make it very complicated also by taking several factors, but in a simple dynamic demand model I have just put it like this. Positive C suggests trend continuation. That means if C is positive, that means it is habit forming product. Means since C is positive, so last time there was some demand, in that proportion you will get new demand also. But sometimes C can be negative also. Negative C suggests stockpiling. That means somebody already purchased lot of quantity and he has stocked it and he may sell in the market. Okay. So, therefore, buying now reduces future demand. Okay. So, this is the type of this one. Now, I am going to discuss one heuristic type of algorithm to tackle the dynamic inventory problem. This is called Silver Meal heuristics. It is a production planning method in manufacturing composed in 1973 by Edward A. Silver and H. C. Meal. If you go to Scholar Google, probably you can get their original papers also, but I am explaining in a very simple way, just pay attention. So, Silver Meal heuristics calculates the average cost per period by considering the setup cost and holding cost over consecutive periods. They consider holding cost and setup cost in the consecutive periods. It incrementally adds future demands to the current order until the average cost per period starts increasing. So, we say first we decide that let me have inventory only for month of July, see that how much average cost I will be encountering, then include that August also. That means your holding cost naturally will increase. Then you see that what is the cost, then you include September also, like that. So, you keep including new things, new time periods till you get the minimum cost. Means after that if you include maybe October also, maybe the cost starts increasing. So, you have to stop there. So, it is the heuristic method because you are not seeing other situations, what happens in November, December. So, therefore, it may not be fully optimal, but more or less it is optimal. That is why it is called heuristic methods. There is no mathematical proof that it will give you best solution. So, dt is the demand in period t, S is equal to setup cost per order, let us say it is constant only, H is the holding cost per unit per period, that is also let us say constant only, N is equal to number of periods covered by the current order, that means current order, if we order, then we can say for how many months it is sufficient. So, N is the number of periods, how many months or how many weeks, whatever period you take. So, this formula is written in a very simple way, the average cost per period for ordering in period t to cover demands up to period t plus n minus 1. So, demand up to that much you have to cover is given by Cn is equal to S plus j is equal to 1 to n hj minus 1 into dt plus j minus 1. That means the demands are different and divide by n. So, you will get the average cost. So, you see that setup cost is divided into number of periods, and this is this one. Cn is the average cost per period when covering n periods, and S is equal to setup cost, H is equal to per unit per period holding cost, and dt plus j minus 1 is the demand in the t plus j minus 1th period, and j minus 1 is the number of periods the unit is held actually. So, we will make one example, then the things will be more clear to you, that suppose I am not putting any unit rupee or dollar, whatever you assume, but I am putting, let us say, setup cost S is equal to 200, maybe $200 you have to spend for setup, and holding cost is H is equal to 1 per unit per period. So, per period it is 1 unit per period, okay, and this is how that it has come, that you know. Then what happens, that demand D1, suppose now we have demands. So, first month that we need 100 units, second month we need 80 units, third month we need 60, fourth month we need 50. This has been given by somebody to you based on the forecasting model. Now, you have to follow certain steps. Now, step 1 will be compute for n is equal to 1. Suppose I just purchase for 1 period, okay, that means I purchase that of that month only. So, that quantity is taken and immediately it is started getting sold also in that month. So, we are not having any holding cost and simply we are having 200 by 1. We can do 200, okay. If you store in somewhat different way, that in the months also, then little bit that cost will be added, but I am assuming as soon as I got 200 say some units, 100 units, and then ultimately that it got consumed. I don't have to hold it because it got into selling mode. And but if you take compute for n is equal to 2, that means you purchase at one go for 2 months, then the setup cost will be 200 only, but since you have purchased 80 units for next month, not for this month, so therefore 1 into 80 will be added. So, 200 plus 1 into 80 by 2, that means 140, then the average cost will be 140 only. Then compute for n is equal to 3 also. So, suppose 3 months thing I purchase right now, 3 months ration has been purchased now. So, this is 200 plus 1 into 80, because 80 kg has been purchased for next month. So, it will be held in your stock for 1 month. So, 1 into 80, but the other thing is after 2 months. So, it has to be held at 2 months. So, therefore, plus 2 into 60 by 3, and this will be 200 plus 80 by plus 120 by 3, that means it will be 400 by 3 and it will be 133.33. Now, let us say that we compute for n is equal to 4. So, we have C4 is equal to 200 setup cost plus 1 into 80, because 80 kg thing you have to keep for next month and 60 kg thing you have to keep for next 2 months, because this demand is only in the third month. So, 2 into 60 plus 3 into 50 by 4. So, if you do that, this comes out to be 137.5. You see that now the cost has started increasing. So, average cost decreases up to n is equal to 3, but increases for n is equal to 4. So, optimal order covers period 1 to 3, that means you order 100 plus 80 plus 60, that means 240 units at the start of period 1. So, this is how it has to be done, and this is a silver meal algorithm. Okay. So, I have told you silver meal algorithm. Another robust algorithm is that, but may be computationally more intensive, that is called Wagner-Witten algorithm. It is a deterministic dynamic programming based method used to minimize the total cost, setup cost and holding cost over a finite planning horizon with time varying demand. It is globally optimal, unlike heuristics like silver meal, which are approximate. So, it is optimal, and you can solve the optimization problem in different ways, but I am telling in a small way that dynamic programming way, where you do the things in steps and stages. Let us try to tell you at least the formulation. dt is equal to demand in period t, and S is equal to setup or ordering cost per order, H is equal to holding cost per unit per period, and T is equal to total number of periods. Ct is equal to minimum total cost up to period T. Fit is cost of ordering in period I to cover demand up to period T. Okay. These are the notations. Now, what is your objective? Objective is minimize the total cost, and total cost is what? Sum of setup costs and plus sum of holding costs. So, this you have to minimize. So, how do you do by dynamic programming way? You initialize set C0 is equal to 0, that means 0 cost before starting, and cost function. The cost of placing an order in period I to satisfy demand from period I to T is Fit is equal to S plus K is equal to I to T minus 1. So, this becomes H into K minus 1 into dk plus 1, and K minus 1 is the number of periods a unit is held. Then minimum cost up to period T is Ct is equal to minimum 1 smaller than I smaller than T, Ci minus 1. That means how much you have spent up to that, how much cost was incurred up to I minus 1, and plus Fit. So, meaning try all possible previous order points and select the one that gives minimum total cost, and continue step 3 for all periods from 1 to T. Determine the optimal order periods by tracing back from the final solution. If you have not understood that this algorithm properly, then this example which I am going to tell you will make the things very clear. Okay. So, example is the setup cost S is equal to suppose 200, holding cost H is equal to 1 per unit per period, and let us say demand is also D1 is equal to 100, D2 is equal to 80, and D3 is equal to 60. Suppose these are the demands given. Now, how do we do that? So, suppose cost of ordering in period 1 to cover demands up to period 1 is 200 plus 0, that means 200 only, and cost of ordering in period 1 to cover demands up to period 2, this will be, so we are in period 1 only, but we are thinking ahead for period 2. So, F12 is equal to 200 plus 1 into 80, that means 280, because holding cost will be now 80 rupees or $80, that this one. So, cost of ordering in period 1 to cover demands up to period 3 is F13 is equal to 200 plus 1 into 80 plus 2 into 60, and this will be 400. Now, suppose we order in period 2. So, we period 2 only, that option is that either you order only for period 2. So, this will be 200 plus 0, or you also cover demands up to period 3. So, this will be F23 will be 200 plus 1 into 260 will be there, and you can have cost of ordering in period 3 to cover demands in period 3 that is actually F33 is equal to 200 plus 0, means you have to pay only 200. Okay. So, these things we have nicely tabulated stage wise. Now, in the dynamic programming we do like that. We say that, suppose we say C1. So, C1 means first this one, that suppose you order in minimum C0 plus F11. Okay. That means we order in period 1 only. So, that means this we can say 200, and now suppose we order C2. Suppose we just calculate C2 in the stage 2 basically. What is the minimum here? Only this one. Okay, period yes, this is C2 minimum C0 plus F12 plus C1 F22. That means you can have 280 plus here that you have period 2. Okay, cost of ordering up to period 2. So, we can have say 280 and then 200 plus 200 means 400. So, therefore, naturally that this will be basically 280 only. Okay, and C3 is equal to minimum C0 plus F13 comma C1 plus this one F33. So, C3 is equal to minimum 400 plus 200 plus 260 is equal to 460, 280 plus 200 is equal to 400. So, therefore, it will be 400. So, minimum total cost will be 400, and therefore, order in period 1 to cover all demands. Order in period 1 to cover all demands, because that gives you minimum quantity. Okay. That means, if you see that C3 you have combination, if you order in period 1 to cover all demand, you have already shown that it is giving 400. So, it is 400 plus 200 if you order, because other option is that you can order up to 200 here and remaining thing you order in the other case, that means 200 plus 260, or you can say that you can order to cover up to period 280, then you have to worry about third unit. So, 280 plus 200, that means 480 it will be there. And if you think about say I have ordered for 2 months now, so this will be 200 plus 260. Okay. So, this is, yeah, this is 200 plus, yeah, 200 plus 280 plus 200. So, 280 plus 200 will be 480, and this one, and it is another option is of course that this one. So, we can actually say that 200, if you are only order for one this one, then it will be 200 plus this one. Okay. You can say that here if you order 200 plus 260. So, this is basically 460, and this becomes minimum becomes 400. So, minimum total cost is 400. So, order in period 1 to cover all demands. So, this way you have to do that one thing. Now, I am just telling you that batch size is, if it is too large, then inventory carrying cost will be more, batch size is too small, setup cost is high. This is the basis of that. Let us do little bit of the sensitivity analysis. Sensitivity analysis TC Q star suppose is under root 2 SHD. We have already said like that, setup cost, holding cost, demand. So, suppose instead of Q star I multiply by some factor x, that means x may be more than 1 or less than 1. That means we give some perturbation to optimum order quantity. So, this comes like this, x into Q star, and with that it will come 1 by x. So, now we can calculate that the cost. So, 1 by x under root TDS by h plus x into under root TDS h by 2, and this will be under root 2 SHD x plus half x into half. So, basically total cost of x Q star is this much, but total cost optimum is this much. So, their ratio comes out to be half x plus 1 by x. But you can see that if x is very near to 1, then this value will be almost 1. So, that conclusion is that it is not very sensitive to Q if Q is close to Q star. That means, but an optimal fixed cost order equals the optimal inventory cost. Now, there are different type of inventories models, okay, depending on the demand we can make different type of model. One is the constant demand model, other is deterministic, and the third one is stochastic. Lead times can be 0 or greater than 0, or it can be stochastic. Horizon can be single period, it can be finite period, it can be infinite period. Products can be one period, it can be multiple product. I discussed that situation also, multiple products also. Capacity can be order, inventory or inventory limits, or no limits on the capacity. Service can be meet all demand or shortage is allowed. So, these are the various possibilities you can have. Okay. Before I close this talk, little bit I tell that inventory is accounted in your balance sheet etc., in your expense and income account, profit and loss account. Suppose you purchase something 50,000, so in expenses you will show that inventory in 50,000, and let us say that you sold that only the inventory worth some 30,000 item. If you sold it, then you can say sales is equal to 60,000, but still that 20,000 inventory is with you. So, therefore, you have to show in closing inventory 20,000, and here you can show that profit is 30,000 because sales was because you sold 60,000, but the actual item was 30,000. So, 30,000 is profit, and then this side 50 plus 30 80, this side 60 plus 20 80, that means these things should be balanced. And suppose then next year if you do that opening inventory is 20,000, 20,000 inventory is there, purchase if you did nil, and this time you sold it at 40,000. So, your profit has become 20,000. So, this is 4,000, and here that income is also 4,000. So, expense and income will match. Okay. So, this type of thing can be done, and this is this one. Now, I conclude this talk here, and next time we will be discussing probabilistic inventory model. Thank you very much for your kind attention. Thank you.